Hello everyone. In this video, we get to talk about the very last topic of Math 1080, which is how do we do calculus on a polar coordinate. And so throughout this section, we're going to work with the polar function that we define back in section 12.2. That I could define my radical coordinate with a function with the inputs being the angular coordinate, or the angle of my rotation. So the first thing we're going to do is talk about how we take derivatives. The sad thing is we can't do what we've done back in Cartesian coordinates, which is just take derivatives normally, and that's because we don't have a nice notion of slope with a polar function. The only time that would be the case is if r was an angle, because as we discussed back in 12.2, the polar curve that represents this function is a line with a fixed angle of whatever theta is. And so let's figure out how we can take the derivative of a polar function. And here's how we're going to do it. So recall from section 12.2 that when we convert from polar coordinates to Cartesian, we define the parametric equations x and y, where x is r times cosine of theta, and y equals r times sine of theta. Well, because I'm assuming that I have a polar function, I can substitute r as my function f inputs theta. And the reason why I care about doing parametric equations is because we learned from section 12.1 how we can take the derivative of these types of functions. We take derivatives of a parametric equation by essentially taking derivative of the function married with y divided by the derivative of the function that is married with x. And so now we're going to play that same scenario with the set of parametric equations. So let's do that. So our dy dx, I'm going to express the g prime of t and the f prime of t in terms of our parametric equation here. The only difference is that this time our parameter is the angle theta, because that is the variable that our x and y is with respect to. And so now I'm going to take derivative of, with respect to theta, of the function married with y and the function married with x. So I'm going to take derivative with respect to theta of whatever I called y, which was f of theta times sine of theta, divided by the derivative with respect to theta of f. Oh, there should be r in there. There we go. Oh no, the r should not be there. There we go. Sorry, I got a little too speedy. Want to make sure I wrote that down right. And there we go. And now to take the derivative of the numerator and denominator, well, I have a product of two functions with the same input variable theta, so I'm going to have to use product rule. Product rule tells me take derivative of the first function times the second function added by the first function times derivative of the second function. And I repeat the exact same work in the denominator. And if I do that, this will be my resulting formula for the derivative. Note that I have a minus here because derivative of cosine is negative sine. So I just moved the minus sign up front to change that from plus to a minus. Now, there is one remark I do want to make with this formula. And the remark that I want to make is, let's say in my polar curve for my polar function, I plug in a particular angle theta naught, and I know that gives me 0. Well, that means we're going to take the derivative, and let's check what happens when I evaluate at that point theta naught. Well, because I know that at theta naught, f of theta naught equals 0, then f theta naught times cosine theta naught will be 0 automatically. Same with f theta naught times sine theta naught will equal 0 automatically. So that reduces down to just the first derivative of f evaluated at theta naught times sine evaluated at theta naught divided by the first derivative evaluated at theta naught times cosine evaluated at that point. Those two cancels out, and I have sine over cosine, which just gives me tangents. And so what that remark is saying, if with my derivative formula I have an angle that makes my polar function equal to 0, then the slope of the tangent line at that angle theta naught will just be the tangent at that point. And so let's summarize that below. Here's our derivative, or the slope of a tangent line, using polar curves. And here's a remark saying, okay, well, at an angle in which I get 0 for my polar function, but the derivative is non-zero, the angle has a slope of tangent theta naught at that point. Now, just like with parametric equations, one thing that we care about is when we check for horizontal and vertical tangent lines. And we typically find horizontal tangent lines, that's when the derivative equals 0. So we're going to find horizontal tangent lines for points where in our derivative equation above, the numerator is going to equal 0, but the denominator does not equal 0. Because if I have the denominator equal 0, I'll have an indeterminate form of type 0 over 0. A vertical tangent line is kind of the flip-flop. I want to check what makes the denominator equal 0 and what makes the numerator not equal 0. But even if I do get that both the numerator and denominator does or does not equal 0, I can still figure out if I have a vertical or a tangent line at that point, and here's why. I could take the limit as theta approach that angle of the first derivative. And the reason why is because if I have a 0 over 0 indeterminate form, I could just use L'Hopital's. Rule. And even after I do my iterations of L'Hopital's rule, I still get that the denominator, when I take the limit, will be 0. And that will imply that I have a vertical tangent line. It will have to show by our definition what that's going to look like. So let's go ahead and do some examples with our new formula. So let's start off normal. Let's find the slope of a tangent line with the circle defined by r equals 10. So that means because I know my polar curve is just r equals 10, 10 is going to be my function with respect to theta naught. And the derivative of a constant is just a constant. Alright, so let's go ahead and plug that into our first derivative formula for polar functions. So f prime theta sine of theta plus f of theta times cosine of theta divided by f prime of theta times cosine of theta minus f of theta times sine of theta. We can make some substitutions and some cancellation. Because I know that the first derivative equals 0, I know that those two first expressions on the numerator and denominator better equal 0. And I also know that f theta naught, which is the function for our polar curve, equals 10. And because I have that in my numerator and denominator, those are going to cancel out near the very end. So I'll have 10 times cosine of theta, negative 10 times sine of theta. I have a 10 on the numerator and denominator, so they're canceled out now. And cosine over sine is cotangent of theta. Alright, and there's our derivative with respect to theta. Now if we're asked to find the slope of a tangent line, we can still do that. So let's say I want to find the slope of that tangent line, let's say when it equals pi over 2. Well, in that case, what I would do is I would plug in pi over 2 into our derivative function and then evaluate. Now cotangent of pi over 2, that's just negative cosine of pi over 2 over sine of pi over 2. And we know that cosine of pi over 2 is 0. We know that sine of pi over 2 is 1. So I'm going to have 0 as the slope of my tangent line at angle pi over 2. Now let's do a little bit more involved example. And let's start off with finding the first derivative and find the slope of the tangent line at pi over 3. So first we're going to take the first derivative. First derivative, we have to take f prime, or the derivative of the polar function, times sine of theta, plus the function of theta times cosine of theta, over the derivative of the function with theta with the polar curve times cosine of theta minus f of theta times sine of theta. So our polar function is the 1 plus sine of theta. The derivative of that will just be cosine. So I can simplify down my derivative as cosine of theta times sine of theta. And I know what the function for the polar curve is 1 plus sine. So I'm going to substitute in 1 plus sine of theta. Cosine of theta. And then I repeat the same work below. I'll have cosine times cosine, so I'll get cosine squared of theta. And then I'll have 1 plus sine of theta times sine of theta. Alright, let's go ahead and try to simplify this a little bit. First thing that I'm going to do is I'm going to distribute that sine in that expression And another thing that I'm going to do in the numerator, while I was tempted to distribute that cosine to the 1 plus sine, the way I'm thinking of simplifying is a little bit easier. Because I see that in the numerator, I have a common factor of cosine. So I can factor that out to give me cosine of theta up front. And what's left behind, I'll have sine plus 1 plus another sine of theta. So I have 2 sine of thetas together. I'll get 1 plus 2 sine of theta. Now let's look at the denominator. In the denominator, I have cosine squared theta. Then I have a minus sine of theta, a minus sine squared of theta. Well, it looks like it's not going to help me out right now, but I claim it's going to because I have cosine squared. And I could quickly solve for that to equal to 1 minus sine squared of theta. Meaning I have cosine of theta, let's write down theta, and then 1 plus 2 sine of theta divided by, and when I do that substitution for 1 minus sine, because of that extra sine squared, I'm going to get at the very end a 1 minus sine of theta minus 2 sine squared of theta. And while it looks bad to plug that into for pi over 3, I'm going to do one more rewriting, and that is because I say that the denominator equals the following. I say it equals 1 plus 2 times sine of theta, and then in my denominator, I say that this equals 2, 1 plus sine of theta, 1 minus 2 sine of theta. And the reason why I got that factorization is because if you pretend that sine of theta is a variable, you have the quadratic 1 minus u minus 2u squared. And that's pretty quick to factor into 1 plus u times 1 minus 2u. Alright, and with that, let's finish up the problem by finding the slope of the tangent line at pi over 3. So now I want to do my first derivative, evaluated at pi over 3. And so I get cosine of pi over 3, 1 plus 2 sine of pi over 3 divided by 1 plus sine pi over 3 times 1 minus 2 sine of pi over 3. Do some evaluations. Sine of pi over 3 is root 3 over 2. Multiply with that 2. I'll get just square root of 3. And cosine of pi over 3 is just 1/2. So I'll get 1/2 times 1 plus 2 sine, or I actually evaluated that to give me square root of 3, over, I have 1 plus root 3 over 2 in the denominator, times 1 minus sine, so I'll have root 3 over 2 times 2, so 1 minus square root of 3. And so now, because of that 1/2 power that is going on, I say that I can move that 1/2 as follows, where that 2 is in the denominator. and then if I and then I can distribute the 2 to give me at the very end a 1 plus root 3 divided by 2 plus root 3 times a 1 plus root 3. And if you alright, and if you went ahead and factored, that should be a minus 1 minus root 3, you'll actually see that simplifies down to a -1. And the reason why is if you FOIL out the denominator, you'll get -1 minus square root of 3. And if you factor out the negative sign, you'll get negative times 1 plus square root of 3, which is the same as our numerator. Alright, so now let's do a little bit more work and tackle some more problems here. Now let's figure out what will make our derivative positive or vertical and horizontal. And so the first thing that I'm going to do is I'm going to check what makes the numerator equal to 0. So I'm going to set cosine of theta times 1 plus 2 sine of theta equals 0. And what that means is, because I have two things multiplied equal to 0, the only way that's going to equal to 0 is either cosine of pi equals 0, theta equals 0, or 1 plus 2 sine of theta equals 0. But note that I can solve for sine, and if you do that, that's equivalent for me figuring out what values make sine of theta equal to -1/2. And for this, I'm just going to list out the values during one period, because the answers will repeat. So we know that cosine will be 0 when I am pi over 2 and at 3 pi over 2. And we know the values that make sine equals -1/2 is if I land in either the third or fourth quadrant of my unit circle, which is, go back up here, which is 7 pi over 6, and then 11 pi over 6. So that's what makes my numerator equal 0. Now I'm going to repeat the same work for the denominator. Alright, so this is true if either 1 plus sine equals 0, but what makes 1 plus sine equal to 0 is when sine of theta equals -1. And then the 1 minus 2 sine, that occurs when sine of theta equals 1/2. So the values that make sine equal to -1, well, that's 3 pi over 2 on my unit circle. What makes sine equal to 1/2? Well, that'll be pi over 6, and at 5 pi over 6. And so before I do any analysis going on, the first thing I check is between the values of theta that makes my numerator and denominator 0, are there any values for theta that are the same? And based on what I have, the only one that's the same is at 3 pi over 2. So that I'm going to have to do a little bit more work on. But for the other points, I can quickly get conclude slope of tangent line, or if it's horizontal or vertical. Remember, horizontal line means that my numerator equals 0, but my denominator does not equal 0. And to have a vertical tangent line, it's the opposite. Denominator equals 0, but numerator does not equal 0. So from this, I can go ahead and conclude my points. It gives me a horizontal tangent line. And so those points are going to be in our polar value. My angular coordinate will be pi over 2. And if you plug that in to our formula for that, you're going to get 1 plus sine of pi over 2, which is another 1. So I'm going to get a value of 2. I'm going to skip 3 pi over 2 because that makes the denominator also equal to 0. And now I'm going to look at 7 pi over 6. 7 pi over 6 sine is negative 1/2, which means I have a radical coordinate value of 1/2. And then the same thing at 11 pi over 6. Again, I have a negative 1/2. So into my polar curve, I get a radical coordinate of 1/2. And I could also go ahead and conclude whether or not I have a vertical tangent line. I skip 3 pi over 2 because at 3 pi over 2, both the numerator and denominator equals 0. I can go to pi over 6. If I plug that into my polar equation, I'll get a value of 3/2. Same thing with 5 pi over 6. Sine will be 1/2, so I'm also going to get a radical value of 3/2. Alright, so now we're going to do a little bit more work, because we have one value that we haven't talked about, which is at 3 pi over 2. And so we're going to have to do a little bit more work to conclude the 3 pi over 2 part. So I'm going to take the limit as theta goes to 3 pi over 2. Now, my recommendation when you have to do this, take the limit from the right or from the left first. And the reason why I recommend doing that is, let's say that I'm going to have a vertical tangent line. Well, recall that the definition of a vertical asymptote is that the limit as x approaches a value from the left or from the right equals either positive or negative infinity. And we learn a way to tackle those types of problems. And so I'm leaving it as 3 pi over 2 from the left in order to help me out with that conclusion at the end. You can do it from the right as well, but for this example, I'll do the limit from the left. So I get limit as theta goes to 3 pi over 2 from the left of cosine of theta times 1 plus 2 sine of theta multiplied by 1 minus 2 sine of theta times 1 plus sine of theta. Now, here comes my thought process initially. Let's look back at our scratch work from before. So, from our work, the first thing I want to ask myself is, alright, so what in the numerator was 0 when I plug in 3 pi over 2? For the numerator, that was cosine of theta. In the denominator, I asked myself the same question. What value makes the denominator equal to 0 when I plug in 3 pi over 2? And that is the 1 plus sign. If I plug 3 pi over 2 in for the 1 plus 2 sine of theta in the numerator, or the 1 minus 2 sine of theta in the denominator, I'm not going to get a value of 0. And so now you're asking yourself, Scott, why are you making that observation? Because I'm going to make my problem a whole lot easier to work with than just doing L'Hopital's rule right off the bat. And here's how I'm going to do this. I know that cosine of theta equals 0 at 3 pi over 2. I know that 1 plus sine of theta equals 0 at 3 pi over 2. So what I'm going to do next is I'm going to use a property of limits way back in Cal 1, saying, and let's make this more clear, add one extra step for more clarity. I can rewrite the expression above as 1 plus 2 times sine of theta divided by 1 minus 2 sine of theta times cosine of theta divided by 1 minus 2, or 1 plus sine of theta. No tricks up my sleeve. I'm just saying, hey, I have two fractions being multiplied, and I'm splitting them up. Now, the reason why I grouped the 1 plus 2 sine with the 1 minus 2 sine, and the cosine with the 1 plus sine, I know that if I plug in 3 pi over 2, I'm going to get a 0 over 0 here. But if I plug in 3 pi over 2 to the 1 plus 2 sine of theta over 1 minus 2 sine of theta, I'm not getting an indeterminate form, which means I could take a limit of that normally. And so now I'm going to use my property of limits that says if I'm taking the limit of a product of two functions, I could take the limit of the first guy that's being multiplied multiplied by the limit of the second function that I'm working with. Alright, and let's dissect this. If you take the limit of the first term, you'll get negative 1/3. If you attempt to take the limit of cosine over 1 plus sine, that's going to give you an indeterminate form of type 0 over 0. Which means I can go ahead and, let's put that away. Which means I could go ahead and evaluate this limit, giving a negative 1/3 times a limit as theta goes to 3 pi over 2 from the left of cosine of theta divided by 1 plus sine of theta. Because this is a 0 over 0 indeterminate form, L'Hopital's rule is fair game for that limit. So I'm going to use L'Hopital's rule to give me negative 1/3 times the limit as theta goes to 3 pi over 2 from the left of negative sine of theta divided by cosine of theta. Now note that I'm no longer in an indeterminate form, because if I take the limit as theta goes to 3 pi over 2 from the left of the numerator, sine of theta, I'll get a -1, which means that I'm not in an indeterminate form anymore. So now I can take a limit. So let's go ahead and take those limits. So for that numerator, if I include that negative sign up front, I'll get that the limit is a +1. Let's erase this to make it not an equal sign and that negative sign there. There we go. Now let's check what happens with the denominator. So I know that if I just plug in 3 pi over 2, cosine will be 0. But let's analyze a little bit to determine whether or not I'm going to get a positive or a negative infinity. Well, let's look at the curve for cosine over 1 period. So first, I note that I'm approaching 3 pi over 2 from the left, which means if 3 pi over 2 is over here for cosine, that means that value for theta is coming in this direction. And in that term, I'm negative. So for my denominator, I'm negative. And I approach 0 as I get closer, meaning I have a positive number that's relatively constant, a very, very tiny negative number in the denominator, which means that part will equal negative infinity. Thanks to that -1/3 up front being multiplied, my final limit will be positive infinity. And so because my left-sided limit equals infinity, in my definition, I have a vertical tangent point here. So my conclusion for 3 pi over 2 is there is a vertical tangent line at angular value is 3 pi over 2. If you plot it into our polar equation, we'll get 0 for our radical coordinate. And there we go. That's how we're going to tackle that type of question when we have to find horizontal and vertical tangent lines. So let's summarize that up. First, I'm going to determine what makes my numerator and denominators equal to 0. I'm then going to check if there's any intersection of those values. For the values that do not intersect, I can go ahead and deduce where my horizontal and vertical tangent lines are. But for the point that I am intersecting, I do have to take a limit and check to see whether or not I get 0 or I get positive or negative infinity. If this limit equals 0, then that means I have a horizontal tangent line. If it equaled positive or negative infinity, like this example, that means I have a vertical tangent line at that point. And that covers taking the derivative of a polar coordinate. But now let's scroll up and let's see how we tackle how to take the integral of a polar coordinate. And this is going to be very similar to what we done at the very beginning of the semester when we found our formulas for region between curves, disk washer method, and all that jazz. So I'm going to pretend that in a region, I'm trying to find the area of a sector in the circle. Since this is an esoteric equation, you can take the equation as I'm taking the radius or the area of the circle, I'm dividing it by 1/2, and to get to the sector that I want, I have to rotate by angle theta. So here's how we're going to handle this. So just like with Riemann sums, we're going to let R be the region that we're working with in figure 2 from A to B, or alpha to beta. And we're going to assume that should be beta, that should be alpha. And we're going to define 2 rays at the endpoints of the region I'm working with. And I'm going to assume that f is a positive continuous function where if I take the difference of those 2 endpoints in my interval, it's between 0 and 2 pi. And now, just like with Riemann sums, I'm going to divide my interval into n equal with subintervals with the grid points 0, theta naught, theta 1, all the way to n. So as of right now in this paragraph, I'm essentially doing the same setup as if I was doing Riemann sum. And then I divide. I'm going to have my width of the rectangle of each sector be defined as the angle of theta I minus the previous term. And the reason why that's the case is so that way I can split my entire sector into individual pieces, and the theta and the way I define the width means that I'm looking at each individual compartment. And the reason why we have to do that, unlike with Riemann sums in the past, is because I cannot assume that the width is uniform because my curves are not a straight line throughout. So that's why I got to do that. And then just like before in Unit 1, my general area equation is going to be the area for a sector of a circle. I'm replacing f r squared r with f theta, but my function evaluated at the grid point, and then multiplied by the width of the sector I'm looking at. And so then I approximate the total area by taking the Riemann sum before. And if I let the limit go to infinity, well, just like with the integral, I in the end get from an approximation to an exact area underneath the curve. And so from now on, I could take the area inside a polar curve by essentially taking the definite integral from alpha to beta of the equation of a sector of a circle. And I can extend this to talk about a region bounded by 2 functions, similarly to how we've done area between regions before polar curves. And so let's figure out how we're going to do this with an example. So we're going to find the area enclosed by one loop in that 4-leaf clove. So my advice whenever you're taking area of a polar curve is always use symmetry. Symmetry is going to be our best friend in most scenarios in this case. And so what I'm going to do in order for me to use my properties of symmetry, I need to integrate over a symmetric region. So here's how we're going to do that. Let's find our bounds for two-step process. First, step 1. I'm going to find the angle theta where my function equals 0. So 0 equals to cosine of 2 theta. Well, we know that my angle for cosine equals 0 has to be landing on the y-axis, essentially. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. You can keep on going with that, and you can even include negative numbers. Negative pi over 2, negative 3 pi over 2, and so on. But that's when 2 times theta equals 0. Let's scroll back down. In order for me to solve for theta, I'm going to divide everything by 2, giving me pi over 4, 3 pi over 4, 5 pi over 4, negative pi over 4, negative 3 pi over 4, and the list goes on. Now here comes step 2. Step 2 is use 2 consecutive angles above for your bounds. And what do I mean by 2 consecutive bounds? What I mean is have a positive angle and then take that angle with a negative sign up front. And note that I'm also choosing pi over 4 and negative pi over 4. A common question will be, why not 3 pi over 4 and negative 3 pi over 4? Well, the main reason why is because 3 pi over 4 is just pi over 4 times 3. If I pick those two as my bounds, I'm just going to get an area of 3 times what I would get if I take the integral of the line with bounds negative pi over 4 to pi over 4. And so with that, I want to work with negative pi over 4 and pi over 4. And let's do our work over here. Alright, so now we're going to take our area and we're going to take the integral of negative pi over 4 to positive pi over 4, 1/2 times our function for the polar curve squared, which is negative pi over 4 times pi over 4 times a 1/2 times cosine squared of theta d theta. Note that 1/2 is a constant with respect to my integral, so I'm going to move that 1/2 up front to give me 1/2 times the integral from negative pi over 4 to pi over 4 of cosine squared of, it should be 2 theta, my bad. So that should be 2 times theta, and that should be 2 times theta. There we go. All right. And so here's why symmetry is going to come into play. This is an even function. And I am integrating an even function over a symmetric integral. Meaning, I can use my properties of symmetry that we learned in Calculus 1 to essentially say, oh, that integral equals the same as 2 times the integral from 0 to pi over 4 of cosine squared of 2 theta d theta. And note that the reason why I'm doing it is I'm using symmetry of even functions. So those are gone now. And there we go. And now I have just dealing with the integral of 0 to pi over 4 of cosine squared of 2 theta d theta. And right now it looks like, well, I'm sort of screwed. That sucks. But I'm taking the integral of a cosine with an even power on top. And if you recall from when we talked about trig integrals, if that is the case, our half angle formulas are going to come into play. So there's our half angle formula if I just had theta. But I can adjust for if my angle is 2 theta by scaling everything by multiplying it by 2. Meaning cosine squared of 2 theta by our half angle formula equals 1 plus cosine to the 4 theta divided by 2 d theta. All right. So now I have an extra 1/2 in there. I'm going to take that out. And now I'm taking the integral of, by linearity, 0 to pi over 4 of 1 d theta plus integral from 0 to pi over 4 cosine of 4 theta d theta. And if I integrated that, I'll get 1/2 times theta minus 1/4 sine of 4 theta. And my fundamental theorem of calculus tells me, evaluate at the upper bound of the integral, evaluate subtracted by my integral, evaluate at the lower bound. And so if I do that, oh, that should be positive. There we go. Let's see, if I plug in 0, I'll get 0 everywhere else. Plug in pi over 4, I'll get pi over 4 plus 1/4 times sine pi, which is also 0. So I get 1/2 times pi over 4, which gives me a final answer for the area of one of those regions, pi over 8. All right, and there's one example of taking the definite integral of a region. Now let's do more interesting, and let's say now I have 2 functions that I'm working with. Now I'm taking the area of the region that lies inside that curve, or inside that region. So just like before, when we talked about area of a region between curves back in Unit 1, my bounds are going to be fixed unlike before, because my bounds are going to have to be where my intersection gets to occur. So in this case, my area is 1/2 times the integral of pi over 6 times 5 pi over 6 of the function that is greater, which in this case is the 3 sine of theta squared, minus the 1 plus sine of theta squared, d theta. All right. And so now let's go ahead and FOIL and expand these two out. If I do, I'll get 1/2 times the integral of pi over 6 over 5 pi over 6 of 9 sine squared of theta minus 1 plus 2 sine of theta plus sine squared of theta d theta. Now, this is going to be nasty to try to evaluate if I'm still left with a pi over 6 and 5 pi over 6. However, I claim that we also have symmetry here, and here's why. If you look at the graph, note that if I split that vertically in half, my region is a mirror image of each other. So I have a vertical symmetry. And now, if you watch the section 12.12 video, I mentioned that if you have symmetry across the y-axis, you can think of this as symmetry around the angle pi over 2. And the reason why I made that note in that previous video is I'm going to use that fact here and transform that into 1/2 times 2 times the integral of integral from pi over 6 to pi over 2 of 9 sine squared of theta minus 1 minus 2 sine of theta minus sine squared of theta d theta. And that's why I made that note. If you have a vertical symmetry about the y-axis and you're integrating, you can still use that symmetry again. Just note that my upper bound will now be pi over 2. Let's go back to the next page and do more work on that. All right, so let's go ahead and copy down that problem. So I have the integral from pi over 6 to pi over 2 of 9 sine squared of theta minus 1 minus 2 sine of theta minus sine squared of theta. I could do some simplification. That gives me 8 sine squared of theta. So that means I have the integral of pi over 6 to pi over 2 of 8 sine squared of theta minus 1 minus 2 sine of theta. And now let's try to simplify our work a little bit. And here's how we're going to do that. I don't like that sine squared there because when I try to integrate, it's going to be a little bit more work. But I can tackle that guy by using my half angle formula for sine. And I'm going to use that now to give me pi half pi 6, the integral, times 8 times 1 minus cosine of 2 theta over 2 minus 1 minus 2 sine of theta d theta. And 8 times 1 half, now simplified down to a 4. So I'm now given the integral of pi over 6 to pi over 2. If I distribute that 4 out, I'll have 4 minus 4 cosine of 2 theta minus 1 minus 2 sine of theta d theta. See common terms there. So I get now inside my integral the integrand 3 minus 4 cosine of 2 theta minus 2 sine of theta d theta. And if I integrate now, I get the following. Antiderivative of 3 will just be 3 theta. Antiderivative of cosine of 2 theta is just sine of 2 theta over 2. But because of that 4, that's one upside down to 2 times sine of 2 theta. And antiderivative of sine is negative cosine. So 2 times cosine of theta. And because I have a definite integral, fundamental theorem of calculus says, evaluate from the upper bound, subtract it from my antiderivative evaluated at the lower bound. And doing that gives me the following. Evaluated at pi over 2, I'll get 3 pi over 2 minus 2 times sine of pi, because 2 times pi over 2 is pi, plus 2 times cosine of pi over 2, minus, evaluated at pi over 6, 3 times pi over 6, but which reduces down to pi over 2, minus 2 times sine of pi over 3, plus 2 times cosine of pi over 6. Now say some simplification gets to occur. So sine of pi equals 0, which means this whole thing is 0. Cosine of pi over 2 is 0, which means this whole expression is 0. Sine of pi over 3 is root 3 over 2. So that reduces down thanks to 2 to a square root of 3. And the same thing to 2 times cosine of pi over 6. So I'll have a minus square root of 3 plus a square root of 3. So those two get to cancel each other out. Meaning I'm left with 3 pi over 2 minus a pi over 2, which gives me a final answer of pi at the very end. And there we go. Now, I gave y'all a graph to find the bounds from the intersection. But what if I'm not nice enough and I didn't give you a graph to work with that? So let's figure out how we figure out the intersections for a curve. So to find a point of intersection using a curve, I set those two curves equal to one another. So I set the r equals 1/2 equal to the cosine of 2 theta. So for cosine of something to equal 1/2, I must end up at an angle where the denominator is 3. So that means on the unit circle, I'll have 2, not 2 pi, 2 theta, equal to pi over 3, 5 pi over 3. And because it's positive, I'm not at the third quadrant. So I'm at 7 pi over 3 and at 11 pi over 3. And then if I divide it by 2, I get pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And so while it's nice that we have some of our values already, pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6, we've actually missed a couple. Because if you graph this curve, we actually have 4 other points of intersection between the curves r equals cosine over 2 theta and r equals 1/2. And these 4 points are given here. So keep in mind that we can solve for this graphically. The hard part is, note that we only obtained 4 points, but we actually have 8 overall. So let's say that we did not have that curve. How can we get those 4 points again? Well, the way that we would do it is we have to use symmetry. And the way to use symmetry is, if I did the circle r equals -1/2, I will still have a circle with a radius of 1/2. And so then I would solve for the equation -1/2 equal to cosine of 2 theta. And now, because I am at a negative value, that means I'm going to have to do my methods there. And I claim when you solve for theta, you will get the -1/2 that we're looking for. So let's determine that. So 2 theta equals -1/2. Well, -1/2 means I'm going to have means I'll have 2 pi over 3. Then I would have to have a 4 pi over 3. And then I would have to have a, let's see, -1/2. That means I would have to have 8 pi over 3. And then a 10 pi over 3. And note that I got the last two by doing another full rotation about the unit circle. And then if I divide it by 2, I'll get the pi over 3, the 2 pi over 3, the 4 pi over 3, and the 5 pi over 3 from before. So note that solving the equation, I'll only get a portion of it. We can get the other curves by either graphing it or using symmetry and then repeat the solving a system of equations. And so here comes a fun exercise that we've done early in Calc 2, and now we're repeating here. So we're going to try to set up an integral to calculate the regions A, B, and C. And let's start out with the region A. First, note that my circle, 3 times cosine of theta in A, is greater than the carodoid, 1 plus cosine of theta. And that's occurring at the intersection pi over 3, starting at 0. So that means my integral is going to go from 0 to pi over 3, 1/2 times first the curve that is larger, so 3 times cosine of theta squared minus the smaller region, 1 plus cosine of theta squared d theta. Alright, and let's now repeat that with the region B. So B is going to be a little bit more complicated. So first off, the bounds of the integral for B, I again start at 0 because at 2 my angle is 0. So in region B, from angle 0 until I hit angle pi over 3, I'm just dealing with the curve r equals 1 plus cosine of theta. So the first portion of the integral is going to be similar to before, but because I'm not dealing with the circle 3 times cosine, it's going to be 1 plus cosine of theta squared minus 0. But in the region B, after I hit pi over 3, now I have a circle coming along the 3 times cosine of theta, coming along and playing a part of it. And in that region that I shaded in pink, the circle is greater. And that's occurring from pi over 3 until I hit pi over 2. So from pi over 3 to pi over 2, the circle is greater, so it's going to be 3 times cosine of theta squared minus the 1 plus cosine of theta squared. And now we tackle the region C. I'm going to trim this off to kind of make it more clear. So, just like with the last portion of the region B, C has that same situation going on. From pi over 3 to pi over 2, I am bounded by 2 functions. In this case, the carodoid is the greater one, and then the circle is the smaller. So, for the first part of the region C, from pi over 3 to pi over 2, 1/2 times the greater function squared, 1 plus cosine of theta squared, minus the smaller one, 3 times cosine of theta squared. And then from pi over 2 until pi, I'm not dealing with the circle anymore. I am just dealing with the carodoid over here. Meaning that all I'm left with is to take the integral of 1 plus cosine of theta squared. And there's my region C. Alright, and from now on, let's finish up with arc length. So, we're going to do the arc length of a polar curve. And I say that just like with the derivative equation of a polar curve, parametric equations are going to help us out. And here's why. Recall from our section on parametric equations that the arc length of a parametric equation is the derivative of the function that is married with x squared plus the derivative of the function that is married with y squared. Well, I now know that I can express x and y in terms of the parametric equation r times cosine of theta and r times sine of theta. And thanks to our general expression for a polar function, I can substitute Rn for f of theta. And also using product rule, I get these following two equations. And so what I'm going to try to do is I'm going to substitute what is appearing inside the square root of the arc length formula for a parametric equation. And so let's determine that. And just a forewarning, at first it's going to look ugly, but I promise it's going to be pretty. Something that I sometimes say to my cousins, but they're not going to watch this video, so I can say that about them inside the video. So let's take the derivative of x with respect to theta squared and the derivative with respect to y of theta squared. So I substitute in my first equation, the f prime of theta times cosine of theta minus f of theta times sine of theta, all of that squared, plus f prime of theta times sine of theta plus f of theta times cosine of theta squared. All right, let's FOIL this sucker out. If you FOIL out the first expression, you're going to get the following. You're going to get f prime of theta squared times a cosine squared of theta minus 2 times f of theta times the first derivative of f of theta times sine of theta times cosine of theta, added with f of theta squared times sine squared of theta, added by the ugly thing that we're going to get when we FOIL out the second expression. And doing that, we'll get the first derivative squared times sine squared of theta minus 2 f of theta times f prime of theta times sine of theta times cosine of theta plus f of theta squared times sine squared of theta. That should be a cosine, not a sine. I cannot read today, and there we go. All right, so right now this looks ugly, but I claim that this is going to be pretty soon. And so here's how we're going to make it a little bit pretty. The first thing I'm noticing, and that should be a plus, not a minus. So let's change that to a plus. And that is with this first expression. So even though I split this down to two lines, this is technically one thing being done. I'm adding all of these together. And so I have 2 times f of theta times f prime of theta times sine of cosine minus itself. Those two get to cancel each other out. here's going to be my next step in the next line. For the two things that I underlined in blue, they both share a common factor of the first derivative of f squared. So I'm going to group those together. And likewise, because the two that I underlined in pink share a common factor of the function f squared, I'm going to group those together and factor out the f of theta. Meaning I get the following. You get f prime of theta squared times cosine squared of theta plus sine squared of theta plus f of theta squared times cosine squared of theta plus sine squared of theta. And I say from here, I win. Because that is just a fancy way to write 1 for both of them. Meaning, the component inside the square root of the formula for arc length for parametric equations, for polar curves, that whole thing just simplifies down to the first derivative of the polar curve f squared plus the polar curve squared. And I get to substitute that in for my formula for arc length, which now gives me, after summarizing, my Knight's formula for the arc length of a polar curve. This integral from alpha to beta of the square root of the polar curve itself squared plus its derivative squared. And let's finish this up by finding the arc length of the cardioid on the interval 0 to 2 pi. Well, let's tackle this guy. So first, from our formula, integral from 0 to 2 pi of f of theta, which is 1 plus cosine of theta, and then its derivative, negative sine of theta. Meaning I have 1 plus cosine of theta squared plus negative sine of theta squared, all inside a square root d theta. So the first thing that I'm going to note is the following. I am symmetric about the horizontal line, and because of symmetry, I can rewrite my integral as 2 times the integral from 0 to pi of the square root of what's inside here. So it's 1 plus cosine of theta squared. And because of that negative, I'm just going to go ahead and change that to sine squared of theta, d theta. Let's follow out the 1 plus cosine. 2 times the integral from 0 to pi, square root of 1 plus 2 cosine of theta plus cosine squared of theta plus sine squared of theta d theta. Let's write that better. There we go. Well, cosine squared theta plus sine squared of theta, that's just a fancy way to write 1. And I have another 1, so combining like terms, I get 2 times the integral from 0 to pi of 2 plus 2 cosine of theta d theta. So I have a common factor of 2 inside my square root. So I can rewrite that as 2 times the integral from 0 to pi to 1 plus cosine of theta d theta. Well, I can take that square root of 2 outside of the integral because it is a constant, and I'm left with 2 times the square root of 2 times the integral from 0 to pi, 1 plus cosine of theta d theta. And right now it looks like I don't win in this case, but I say we still do, because I can use my half angle identity to help me out. Because so far I have 1 plus cosine of theta, that should be 2 theta. There we go. And I can use that to help me, because if I multiplied both sides by 2, then that means I canceled out the 2 on the right hand side of my half angle formula, meaning I just have 2 times cosine squared of theta equals 1 plus cosine of 2 theta. But that's not what I have inside my integral. I have 1 plus cosine of theta, meaning using my half angle formula, the angle that was inside the cosine squared must have been theta over 2. So that way I can have cosine of theta popping in the right hand side. Alright, and now that I know that 1 plus cosine of theta equals 2 times cosine squared of theta over 2, I'm going to now use that fact and substitute in 2 times cosine squared of pi over 2 for the 1 plus cosine. Alright, and thanks to that square root, I'll have square root of 2 times cosine of theta over 2. 2 times the square root of 2 times another square root of 2 gives me 4. Integral from 0 to pi. I have cosine of theta over 2 d theta. So that gives me equals to 4. Antiderivative of cosine of theta over 2 is 2 times sine of theta over 2. Fundamental theorem of calculus says evaluated at pi subtracted by 0. Sine of pi over 2 is 1. So I get 2 multiplied by 2 for evaluating at the upper limit. And sine of 0 is 0, so at the upper limit I just have a 0. Meaning my entire arc length for that cardioid over the units over 1 rotation equals 8 for our arc length. And with that example being done, this is the end of Math 1080. That is the last example and the last section for this course. So, thank you all very much for surviving throughout this semester. You've made it. Now all we have left is to tackle the final. Alright. And that's all we're going to have for this semester. Hope that you finish strong. And if you can, make sure that you smash that like button and make sure that you subscribe to my channel. So hopefully I can get monetized by YouTube and get sponsored by Raid Shadow Legend. Alright, see y'all.